There we go. Okay. So welcome to the July meeting of the Stockton Astronomical Society. I'm Tim Clark. I'm the president, and I want to welcome you all to the meeting. And we're going to jump right into introduction of our speaker for tonight. Dr. Kathryn Plant studies high energy cosmic rays, searching for the origins of the Milky Way's fastest particles. She is a NASA postdoctoral, should be sharing my screen, postdoctoral fellow at the Jet Propulsion Laboratory in Pasadena, California. She received her bachelor's degree in physics from the University of California at Santa Cruz, and then contributed to an upgrade to the Molongo Observatory Synthesis Telescope in Australia before completing a PhD in astronomy at Caltech. Her work also focuses on techniques for processing large amounts of radio data, and she is involved in the collaboration for astronomy, signal processing, and electronics research, which makes tools for processing radio data more accessible. Hopefully we'll hear more about that. So please join me in welcoming Dr. Kathryn Plant.
Thanks very much. Should I share my screen now?
And I'll stop sharing and turn it over to you. Okay.
Are my slides showing again?
Yes.
Okay. Yeah, so I'm going to talk about cosmic rays, which are high energy particles coming from outer space. And they're otherwise ordinary subatomic particles like electrons, or in the case that I study, they're atomic nuclei, protons, and nuclei from heavier elements. And they would be ordinary, except that they've somehow been accelerated to nearly the speed of light. And the puzzle is, what does this, and where do they come from? Sorry, it's not advanced. There we go.
Mm-hmm.
So for a while, cosmic rays were actually the best way to study particle collisions at all. They were very important in the early history of particle physics. And this was until particle accelerators in laboratories were built in the 1950s. And so this is a photo of the Large Hadron Collider at CERN. And it can accelerate a proton to 99 with 8 nines after the decimal place % of the speed of light. And that's about 1,000 giga electron volts, where an electron volt is the amount of energy that an electron gets when you apply 1 volt of electric potential to it. But the most extreme cosmic rays, however, are millions of times higher energy than this. And so they are a window into physics and environments that are still far beyond what we can study in a laboratory on Earth. And because I know this is probably a group with a lot of range of backgrounds, there's students in the room, I always like to start with a brief reminder about how energy works, what energy is. There's different forms of energy, and kinetic energy is the energy that comes from an object's motion. It goes as the square of the velocity. And then there's also what's called rest energy, which is the energy that the object has even when it's not moving. And this is the energy that pulls down a scale in a gravity well. And this energy has a familiar equation to describe it. Ooh, I don't know what happened to this equation, but it sort of got expanded. But this is the E equals mc squared energy, is the rest energy. And for a proton, the rest energy is about 1 billion electron volts, 1 giga electron volt. But proton in the Large Hadron Collider would have 7,000 times more kinetic energy than its rest energy. In all of our everyday objects that we encounter, the kinetic energy, the energy from the object's motion, is always way, way less than its rest energy. But that's not the case with these high energy particles. They're going so close to the speed of light that way more of their energy is in their motion than in their mass. And the highest energy cosmic rays ever observed have come from something somewhere in the universe that can accelerate a particle so fast that one single atomic nucleus has as much energy as a fast-pitch baseball. And now, a fast-pitch baseball, that would hurt to get hit with, but that doesn't really sound like an astronomical figure. And so to explain why that is a lot for one proton, the difference in mass between a proton and a baseball is about the same as the difference in mass between a baseball and the Earth. So if a pitcher could accelerate a baseball to the speed of these atomic nuclei, the baseball would have as much energy as if the whole Earth were speeding towards the baseball bat. And so then the next point to talk about is, how do you find out about one individual proton traveling this fast? We need it to leave clues behind. It's very difficult to catch the individual particle itself. And this is one of the things that I really like about astronomy and astrophysics, is that we have to find ways to measure things that are beyond what we can easily see or put a yardstick up to. And so I personally really like understanding techniques for how to observe things and how to go beyond the optical astronomy and observe at other wavelengths and with other particles. And so the story of cosmic rays goes back to the beginning of particle physics. And in the late 1800s and early 1900s, radioactive elements had been discovered, but people still hadn't figured out what was the radiation that the radioactive particle emitted. And so they developed various techniques for measuring radiation from radioactive elements. One of these is called an electroscope. And the way that it works is that a high energy particle, whether it's radiation from radioactive decay or a high energy particle from space, high energy particle will, as it passes through the air, it will rip away some of the electrons in the air molecules and ionize them. And normally air is a good insulator, but if it's ionized, it can conduct electrical current. And so an electroscope would be this box with a probe with two flexible pieces of metal that when you apply some charge to this metal probe, the two leaves at the bottom will be filled with like charge that will repel. And so the leaves will spread away from each other. But if something ionizes the air in the box, then that charge will be able to conduct away and the metal will go back into its unbent position. So this was a way to measure ionizing radiation, and people were using it to study radioactivity. But they noticed that even when they put their radioactive sources away, the electroscopes would slowly discharge anyway, even when there was nothing, no known source of radioactivity present. So they first they thought maybe it would be trace radioactivity in the Earth that was causing this to happen, and they tried packing lead around the boxes to isolate them, because lead blocks a lot of high energy particles just because of how dense it is. And the electroscope still discharged. So that meant that whatever this was had a lot of energy. But to test the idea that maybe it was coming from something in the Earth, they tried taking it up tall buildings, and that didn't work. a really tall building had just been built, the Eiffel Tower. And so somebody took one of these up to the top of the Eiffel Tower, and it was still discharging. So then eventually in 1914, Victor Hess took one of these in a balloon and went up to almost 20,000 feet and found that the flux of this radiation actually increased the higher you go in the atmosphere. And so he said it must be cosmic, and hence we call it cosmic rays. And as I mentioned earlier, until particle accelerators and labs were built, cosmic rays were really useful in the early history and development of particle physics, because they were our only source of high energy particles to collide. And as an example, they were important in the discovery of antimatter. And so another way, other than the electroscope, a more sophisticated way to study these high energy particles is to have them travel through some kind of material that leaves a track. A cloud chamber is one way to do this. You have a fine mist of particles that's right on the edge of condensing, and a little bit of ionizing radiation will give the vapor something to condense around and leave a little trail of denser mist in the cloud. You can actually do this at home with dry ice and rubbing alcohol. I highly recommend looking up the instructions for it on the internet. It's a really fun experiment to do at home. You can see cosmic rays yourself. Maybe some of you have already done that. But then certain kinds of photographic plates would also leave a trace of the part. And so this is a photographic plate from the discovery of a positron, and it's that curved arc passing through. And they had a magnetic field present that would make the particle's trajectory curve, and that could tell you about the ratio of the charge and the mass. And so it was found that there's a particle that has the mass of an electron, but the opposite charge. It was called a positron, and that was the first example of antimatter being detected, and it was detected from cosmic ray particle showers. And, oh, was there a question? Okay, sorry, I thought I heard this question. Yeah, and so coming back to the present day, some of the big picture questions are still at the highest energies. Where do cosmic rays come from? And what is the highest energy cosmic ray that the Milky Way can produce? Because some of these come from inside our galaxy, some of them are outside our galaxy. And where does this transition happen is another key question that I'm especially interested in. So here's a plot of the cosmic ray spectrum, which means on the y-axis, the value represents the rate that cosmic rays are arriving in a measurement area, and the x-axis, the lower axis, is the energy of the particle. And so cosmic rays become more and more rare at higher and higher energies. It's a remarkably steady decrease. And this is surprising because it doesn't seem possible for just one type of source to be responsible for this whole spectrum. And so it's remarkable how smooth it is. And that may be because there are some common processes that might be involved in different kinds of sources. And this is showing data from several different kinds of experiment techniques put together. The red points are measured in space. The blue points are measured from the ground. And you may notice at the low energy range, it looks like there's this jump. Like everything has been very smooth, but then how come the line doesn't connect? And that's because this lowest energy data is coming from Voyager. And Voyager is, all of the other experiments are measured right at Earth, but the Voyager spacecraft has actually left the sun's influence of the solar wind. Solar wind helps direct and deflect particles. And so there's this jump in the spectrum because Voyager is actually making a measurement of a slightly different spectrum in a different place. And it's the only experiment we have that can tell us about the environment outside our solar heliosphere. Yeah, and so these lines are just to give kind of a intuitive sense of the flux at these energies. You have 1 cosmic ray per square meter per second, going down to 1 per square meter per day, and then 1 cosmic ray per square kilometer per year. And so you need different techniques to study cosmic rays in different parts of the spectrum, because in the energy range where you have cosmic rays per square meter per second, you can launch a small detector into space and detect them. But if you're only going to get 1 per square kilometer per year, you have to build experiments on the ground so that you can cover really large areas, because you can't launch a square kilometer detector into space. And also for reference, this arrow is the maximum energy that the LHC can study. So just to give a few examples of modern cosmic ray detectors, I mentioned Voyager. There are a whole bunch on that previous slide, but just to show photos of a few different types. At the lower energies, you can put the detector in space and detect the cosmic rays directly. And one example is an experiment called ISS CREAM. It's on the International Space Station. And then at the highest energies, cosmic rays have to be studied from the ground. And so that I have two different photos of an experiment called telescope array. Sometimes scientists give things boring names, but this one is just called telescope array. It's out in Utah, and they cover 300 square kilometers with different types of detectors. The 300 square kilometers are solid covered, but because the detector can view, each one can view an area. So they can be a little bit sparse, but they are observing 300 square kilometers in order to detect the really high, really rare, really high energy, really rare cosmic rays. And they use detectors of different types. So these flat brown boxes on the ground in the lower picture are detecting particles directly, but they're not the original cosmic ray particle. They're the aftermath of a collision with the particle hitting the atmosphere. And then the telescopes in the top picture are looking for faint flashes of light as air molecules get energized by the shower of high energy particles passing through. They will fluoresce. And so the telescopes look for very faint flashes of light in the atmosphere associated with cosmic rays arriving. And later on, I'll be talking a lot about another technique, which is radio observations. But so for a little more context, why are cosmic ray sources so hard to pinpoint? Why, if we have all these detectors, why can't we just collect some cosmic rays and then look at where they came from and know what makes them? And that's because charged particles turn in magnetic fields. And so if we see a cosmic ray arriving from a particular direction, that it has traveled through the magnetic fields in the interstellar medium, and the direction that it arrives from isn't the direction it started out from. So if a cosmic ray would travel on this red line, which you can see when it lands on Earth, you can see which direction it came from, but that doesn't tell you where it started out. It's very hard to trace the path back through the magnetic field. And so to deal with this challenge, we need information from several kinds of sources. Cosmic rays, when they interact with gas in the interstellar medium, can produce gamma rays and neutrinos. And since these are neutral particles, gamma rays are photons, and neutrinos are their own particle, but they don't have a charge, they travel in straight lines. And so they would be clues for where cosmic ray sources might be, or at least where the cosmic rays interacted with something. But there are various things that make gamma rays, and so you can't just look for the gamma rays to know for sure you found the cosmic ray sources. And then the cosmic rays themselves still provide really important information, because even though you can't trace an individual particle back to its source, making measurements of the population as a whole looking for shifts in mass composition, looking for features in the spectrum, gives you information about the types and number of sources that there might be. And so now I'm going to go over some of the places that we think cosmic rays are coming from. And starting at the lowest energies, it is pretty clear that they mostly come from supernova remnants. And when a star that's about 10 times the mass of the sun or larger runs out of fuel, it explodes in a supernova. These explosions can glow so brightly that for a short time they might outshine that star's entire galaxy. And the remnant of the explosion, not the explosion itself, but what's left behind, has all of the ingredients that you need for accelerating cosmic rays. This is a picture of the Crab Nebula, which is a remnant of a supernova explosion from 1054 AD. It's about 6,500 light years away. And this picture was taken with the Hubble telescope. You see this complicated gas structure, and it's full of shock waves. Shock waves can accelerate particles because when a particle flows through the shock, it gets a boost of speed. And then if there's a strong magnetic field in the region making the particle turn, it can make the particle turn around and go back through for another boost. And so gradually, over a fairly long amount of time, with a large number of small boosts, particles can get accelerated up to the speeds of cosmic rays. However, models and observations suggests that cosmic rays in supernova remnants can't get much more than 1 million giga-electron volts. And so up to about that energy, it's quite possible that supernova in the Milky Way are the main source of these particles. These particles are coming from inside the Milky Way, but higher than that, higher energies than that, need other models. And at the highest energies, one good idea is the jets that flow out from the vicinity of the supermassive black holes in distant galaxies. Although not actually too distant. These particles don't travel across the whole size scale of the universe. So it still needs to be in somewhat our galactic neighborhood, but far outside the galaxy. Most galaxies, including our own, have a supermassive black hole in the center. And in some galaxies, not our own, there's a lot of gas flowing onto that black hole and falling into it. And the jets that you see in the photo, they aren't launched out of the black hole because nothing escapes black holes, but they're launched from the process of the gas trying to swirl into the black hole, kind of like water going down a drain. And then with enough energy, there can also get some that doesn't fall in and gets launched out. And then it has a series of shock waves and the right kinds of conditions to potentially accelerate particles to much higher energies than what supernova remnants can do. This picture is from a galaxy called Hercules A. And it's a composite of two very different kinds of images. There's a Hubble image, which is taken in visible wavelengths of light. And then the purple that's overlaid was made with the Very Large Array, which is a radio telescope, and it's showing where the radio emission is coming from. And so in Hercules A, the radio emission is actually not brightest at the center of the galaxy. It's brightest in these big jets that are launched out of the black hole. And the radio emission comes from cosmic ray electrons, which, when they're in a magnetic field, will glow with what's called synchrotron radiation. And so the fact that we know for sure from the radio data that there are cosmic ray electrons there is one of the reasons we think it might be a source of some of the highest energy cosmic ray protons. But that doesn't guarantee it for sure. People are still looking for more sure evidence, like neutrinos and neutrinos or very clear gamma ray evidence. There's a lot of pieces still put together to confirm this, but this is one of the best hypotheses for where the highest energy cosmic rays come from. Not necessarily this particular galaxy, but galaxies like it. But in between the extremes of supernova remnants up to a certain energy within our galaxy, and then jets from black holes in other galaxies, there's kind of a gap where I showed that falling spectrum of cosmic rays getting more and more rare, and the supermassive black hole jets don't do a good job of supplying enough of the cosmic rays right at the energy where supernova remnants are running out of energy. So we probably need another source to fill the gap. And here's a few different ideas of what that could be. I'll talk a little bit more about each of them. It could involve pulsars, which are the dense core of a star that's exploded in a supernova. There are examples in the Milky Way of small black holes with gas flowing onto them from a star that act like a miniature version of the jets in other galaxies. And then there is what's called galactic winds. So a little more about neutron stars. They're a core that's left behind after a star explodes in a supernova, and they're made of tightly packed neutrons, so dense that a mass a bit larger than the sun is packed into a space the size of a city. And they can have extremely strong magnetic fields and can rotate very fast. If they're when they're emitting light from their poles, kind of like a lighthouse, they're called pulsars because we see a flash regularly, like a clock ticking in, and it's visible sometimes in radio emission and sometimes in gamma ray emission. This image in blue is a X-ray image that has been pieced together with several images over time. I think the whole thing is about 6 months, so it's very sped up. But an X-ray image of what's called a pulsar wind nebula, and kind of shows shock waves moving out from near this neutron star, and this is at the very heart of that supernova remnant that I showed earlier. So these might have the conditions for accelerating high energy cosmic rays, but it's not clear whether the magnetic field is actually so strong that they would lose all their energy to synchrotron radiation before they even get to cosmic ray energies. Another possibility is, another piece of evidence that makes pulsars interesting is that they can have these halos that are bright in gamma rays. This is a gamma ray image made with very high energy gamma rays that were detected with this telescope called Hawk down in the lower left. There's water in all of these tanks, and then detectors that will detect when a gamma ray interacts with the water. And this is a map of the vicinity around two pulsars, and the white and then yellow and then red and then blue go from brightest gamma ray emission to faintest. And down in the lower right is the size of the full moon to scale. So if we could see the sky in gamma rays, this pulsar would have a huge halo around it. Another possible source that I want to mention are what's called X-ray binaries, and that's where a fairly ordinary star is overflowing onto either a neutron star or a black hole, and it forms a situation similar to what happens around the black holes, the supermassive black holes in other galaxies, but it's smaller and scaled down. And occurs in our own galaxy, it's an interesting possibility for something that could bridge the gap. And then another possibility is, instead of very dense, strong magnetic field locations, considering very slow acceleration over very, very large distances, and the shocks and magnetic fields in galactic winds might do that. This is a Hubble image of another galaxy, not our galaxy, but the red shows outflows of gas flowing out of the galaxy, and it has a complicated structure of shocks and magnetic fields that might potentially accelerate cosmic rays. And so now putting all of these ideas together on a plot, you can compare potential cosmic ray sources by considering their size and their magnetic field, because a cosmic ray accelerator needs to confine the cosmic rays within the accelerating region until they reach their highest energy that they escape with. And magnetic fields are good at doing that confinement. If you have a weaker magnetic field, but it persists over a longer region, then that can still accelerate high energy cosmic rays. And so the solid and dashed lines are different particle energies, and the shaded regions are the regions that different objects occupy on this plot. You have AGN are the active galactic nuclei that I mentioned, the jets flowing out of, well, this is the blue is the centers of the galaxies, and then the brown is the jets flowing out of them. Neutron stars are way over here. Supernova remnants down here, and galactic wind way out on the size of large sizes and low magnetic field strengths. Now I'm going to, for the rest of the talk, I'll talk more about studying cosmic rays from the ground, and particularly the approach that I'm using to study them. So when a cosmic ray hits the top of the atmosphere and collides with a molecule of air, it starts this sort of domino cascade of collisions, where all the outputs of the collisions are still high energy particles that make more collisions and so forth. And so if yellow is the showing where the particles go in this cascade that eventually kind of peters out, there's several ways to observe it. There's some particles, like electrons and positrons, and also muons, make it to the ground. And so you can put particle detectors directly on the ground. And then the cascade also energizes the air around it, and you can detect fluorescence from that. And sometimes you can directly detect Cherenkov emission, which is the light equivalent of a sonic boom. And now you're maybe thinking, oh, a sonic boom happens when something travels faster than the speed of sound. Nothing travels faster than the speed of light. So how does that happen? It happens because nothing travels faster than the speed of light in a vacuum. But if you're in a material that's not a vacuum, like air, light actually travels a little slower, and it's possible that the particle is going faster and creating Cherenkov radiation. And then all of these charged particles accelerating in the atmosphere create radio emission. And the nice thing about radio antennas is they work even when it's cloudy, and they're a lot cheaper than a lot of these other detectors. And so and then they actually also have an advantage that they depend on the parts of the air shower that we understand the best. And so you can make some very nice precise measurements that you can trace back to information about the primary cosmic ray. And so I've worked on and for my PhD thesis, I built a detection system for studying high energy cosmic rays with radio antennas, and I'm still using that now in my work at JPL. But all of these different detection techniques have certain sort of to-do list to them. The air showers from cosmic rays are very, very fast events. So you need a way to search for these really fast things and save the data. And then there's some data processing to do of filtering out backgrounds and interference. And then when you have the good clean data, you want to reconstruct information about the original particle. That's its energy, and the depth in the atmosphere where the interactions happened is actually a proxy for the mass of the particle. And then eventually you can estimate population information from a large sample of these. And you're asking me a bit at the beginning because of the photos. I've already kind of introduced the Owens Valley Radio Observatory. It's in Eastern California, in a deep valley between the Sierra Nevada and the White Mountains. And it's an array of dipole antennas. So there's 352 antennas that look like this. And over the last 4 years, there was a huge upgrade to the array. This is just kind of a collage of photos of different parts of building antennas. And we had 352 times 2 because it's both polarization. So 704 cables to plug in and so forth. And now it's ready for searching for cosmic rays. And to find cosmic rays, what we're looking for is a 10 nanosecond flash of radio waves. This is a movie slowed down of cosmic ray emission sweeping across the array. This was from actually from a prototype run from before the upgrade. And the color and position of each of the spots is the position of an antenna. It's actually just zoomed in on one part of the long wavelength array. And so the color and size of the spot will be how much radio power is arriving. Now, if I play the movie, you'll eventually see something sweep across the array. And but if you notice, that's the time axis is counting in nanoseconds. So the whole thing is very fast. And to search for these 10 nanosecond flashes, we bring data from all of the antennas back to a central location, and we bring it back on a mix of copper cables and optical fibers, but it's not digitized yet. We do all the digitization and signal processing in this white building. It's actually a converted shipping container in the center. But bringing all of the antennas back to a central location is something that a lot of other arrays haven't managed to do, and having everything in one place lets you compare signals from different antennas, and it's been really useful in the search process. But the total data output, raw data output from all of these antennas is about a terabit per second, which is 0.1% of the total global internet traffic. And so we can't stuff all of that into the computers to sort through later. We have to make very fast automated decisions about which data to save. We can't even put all of it into the computer in the first place. We have to use a different kind of electronics for deciding when to save data. And this is challenged by there being lots of other things that make fast flashes of radio emission. Most of them are things that people do. TV stations, radio, like FM radio, where we observe at frequencies that are just below the FM radio band down to from about 30 megahertz to 80 megahertz. And the TV and the radio are mostly sources of steady emission, but it can still, it can look like a flash if it reflects off of something. Airplanes make fast flashes of emission. And sometimes you have TV stations bouncing off airplanes. And then faulty electrical lines from power lines make a lot of radio frequency interference. And this is the worst for the cosmic ray system because it really does make nanosecond flashes. So it's kind of a search for needles in a haystack, where you have thousands of events every second, and we are expecting 5 cosmic rays per day. And so to do this, there's some processing that has to be done before we even put the data in a computer to decide if the data is worth saving. And I set this up on something that's called a field programmable gate array. And so when you run code on your computer, it has been compiled from human readable instructions down to a process for doing your computation as efficiently as possible on the computer hardware that you have. But what if you could reconfigure your computer hardware to be really good at just that one job that you want to give it at that particular time? That's what a field programmable gate array is. It's good at doing things very fast. It's good at doing parallel processing, where it's doing the same thing to several streams of data in parallel, but it doesn't switch between different programs quickly the way a computer can. But so it's good for this handling of the raw output of the ADCs, processing a lot of signals in parallel and only saving the bits that look interesting. And since all of the signals come back to that central shelter, one thing I do is I use the fact that radio emission from cosmic rays is kind of beamed like a flashlight. It doesn't light up all of the antennas equally. It'll be like a narrow circular or elliptical flashlight beam has pointed at a particular part of the array. And so I can use the distant antennas to veto RFI, because so this is a map where I didn't mention earlier, the array has a very dense core with a lot of antennas right next to each other, and then sparser antennas. And then I use the distant ones to reject RFI. And this is a simulation of cosmic ray emission overlaid over the map of FIB4. The way the cosmic ray search works is it buffers 20 microseconds of data, of the raw data, and then along the way, it does a search for, well, it applies delays to take into account the effect of all of the cables. Then it applies a filter and some smoothing and looks for pulses above a certain threshold, and waits a time according to the time that it would take light to travel the distance between a group of antennas, and checks whether enough antennas all saw the same thing within that amount of time. And then if at the same time, if there wasn't a veto, it will read out the data. And one challenge in this was being able to save data from every antenna at once, because the antennas actually have to be divided into subgroups to be processed by different FPGAs. And so they needed a fast communication between them, so that if any of them see it, they all send the data. That involved just wiring the boards directly together instead of I was trying to use an Ethernet, or thinking about using Ethernet at first, but it's actually too slow. So they're just wired together with a 1-bit signal going on a wire. And now this upgrade that included adding the whole cosmic ray system is finished. And here's a cosmic ray sweeping across not just the core of the array, but the whole upgraded array. And to show it, because it's over such a larger scale, I'm plotting the point at the arrival time, but then I hold the point on the plot, because if I showed sort of like the movie I showed earlier, if I made the spot disappear, it would be, it's such a larger size scale that's being shown that the flash would be too fast to see. So that's why the format of the movie is a bit different from the other one. And yeah, here are a few more details about that example event. This is the waveform that we saved, and This is a map of the signal-to-noise ratio that shows that elliptical footprint that is the pattern you expect for cosmic rays to illuminate the antennas. Now over the last several months, the cosmic ray search has been running and starting to get ready to build up enough of a sample to start tackling the science questions with. So I'll conclude my talk here and happy to answer questions.
Not a question, but just very, very cool. Thank you for sharing.
Yeah, it's been great. Okay, you guys can, anybody can come off mute and we can talk with Dr. Plant and ask our questions. I do have a question. I'll get it started here. You talked about the high energy cosmic rays coming and hitting Earth at different points. Do I assume that our Earth's magnetic field would act as a shield to prevent a lot of these cosmic rays from hitting the surface? And I guess my question is there points on the Earth that are more vulnerable or more likely to get hit by cosmic rays than others because of that magnetic field that we have at the poles mostly?
Yes. Yes. So the Earth's magnetic field does deflect and redirect cosmic rays. The higher the energy of the cosmic ray, the more of a turning radius it needs. And so at the energies that I'm studying, the Earth's magnetic field is strong enough to make it turn, but the size of the Earth is too small for it to have had much turning radius to go through. And so at this energy range, that doesn't matter so much. But the lower the energy you go, the more that would matter.
I see. Well, I was trying to relate that to a presentation we had a couple of years ago where we had some technicians from the neutrino detector at the South Pole detecting neutrinos. And so there was a reason why they were at the South Pole, because that was I guess the highest likelihood of access for a neutrino to come in at the poles. So do high energy particles, are they more likely to hit at the equator or at the poles? Or, I mean, some of those arrays you had are in Utah or in California here. So is there a function of our latitude or anything like that?
Yes, it's a little bit of a function of latitude, but other considerations end up mattering more, like where can you find the right size of land that's mostly flat, or in the case of the Owens Valley, it's really useful that we have those two tall mountain ranges shielding us from radio emission from cities. And so there is an effect. The neutrino detector at the South Pole also needed to be in a cubic kilometer of ice. And where are you going to find that? And so yeah, you're absolutely right that the Earth's magnetic field does some redirection, but the higher energy you go, the less that matters. And even at moderate energies, there's still other considerations that make it worth building a experiment in a certain place.
I see. Very good. Thank you.
Hello, this is Eric. I have a question. I was able to join the meeting, so I'm glad to have been able to catch your talk, Kathryn.
Thanks.
My question is, if I'm not mistaken, protons are the more abundant particle within cosmic rays. And I guess my question is, why is that? Because I would kind of think that electrons, given their lower mass, would be easier to accelerate than the protons would. Do you have an answer for that question?
So electrons are easier to accelerate, and that also means they're easier to decelerate. So for to measure a cosmic ray here at Earth, it has to make it to Earth without losing all of its energy along the way, and it's harder for electrons to do that. There still are quite a few cosmic ray electrons, especially at lower energies, but electrons lose their energy faster. They don't survive as long as when they're cosmic rays as protons do.
Oh, I see. Okay, very good.
If I could ask another question, Dr. Plant, could you go back to the slide where you show us the nanosecond flash plot? And my question about that was, when you showed it to us, they came up in blue.
This one or the trace of
the animated movie one. That's it, I think.
Yes.
Yeah. They came up in blue, and blue on the scale on the right axis shows fairly low energy. So are you capturing like a supernova remnant flash there, or is there a way to tell what the origin of that was by the energy that you recorded?
Yes. So this one is this beam isn't perfectly aligned with the center of the array, and you can see it's actually getting a higher energy as it goes to the edge. So we might be getting sort of
some distortion.
Clipped by, not distorted, but we might just be seeing, imagine like here I've drawn the beam landing in the middle of the group of antennas, but if you shift that flashlight beam and sweep it across just the edge, then you wouldn't see the brightest part of the beam. So that's part of the effect. We're kind of looking at the edge of that ellipse. And then as for the energy range, that one was between 10 to the 16 and 10 to the 17 electron volts, most likely. And we can't, this is the mystery energy range where we don't have a clear answer of did it for sure come from a supernova remnant, or did it have to not come from a supernova remnant? It's in that gray area.
I've got a question. So we talk about cosmic rays as being both photons can count as a cosmic ray if it has enough short enough wavelength or high enough short enough frequency, or a nucleus or a proton can count as a cosmic ray if it's moving fast enough. How do you discern the difference if they're both the same? You take a photon and a proton, but they have the same amount of energy, because that's what's deciding whether it's a cosmic ray or not.
So I don't call photons cosmic rays, but there are contexts where people do. There are contexts where anything with a certain amount of energy is a cosmic ray.
Okay, because that's what I'm saying.
Most often cosmic ray is referring to the charged particles, the protons and heavier nuclei and electrons. But the reason they sometimes get lumped together is there are some detection techniques that are similar, whether you're looking for a proton or
the same energy level,
or a gamma ray. Yeah, they'll both make an air shower. And then the way you tell the difference is the content of the air shower, that cascade of particles, the content of electrons and muons is different depending on whether it was a neutral particle to start with.
A proton versus a proton. Okay.
Yeah.
Okay, that makes sense. Thank you.
Dr. Plant, how may some of the results of your research manifest in practical applications in the future? I assume like shielding for space travel, space vehicles would be one to shield them from high energy particles, but what other aspects or what other examples might you provide that tell us what your research could yield in the future?
I think so. I think a good motivation for cosmic ray research is really strongly tied to the bigger picture questions that it can answer about how the universe came to be the way that it is, why are galaxies the way that they are. There's evidence that the rate that galaxies form and evolve strongly depends on what cosmic rays in them are doing. And so, this isn't research that has a direct near future device to build to apply to something else. I think they're at lower energies where cosmic rays are more abundant. There are some really cool things that you can do with them. People have sort of X-rayed the pyramids by putting muon detectors in chambers in the ground floor of an ancient pyramid. You can search for hollow places above it because just like an X-ray, the denser parts of the pyramid absorb more of the particles, and if there's a void, more of them get through, and you can kind of map out. People have done this with like lava tubes and volcanoes and pyramids because you can't put something like a pyramid in an X-ray machine in the lab. So there are creative ways that people are using cosmic rays, but mostly at the lower energy range where they're more common.
I see. Well, excellent. Clearly very important work in solving some of the mysteries that our universe gives us is hopefully something that you're going to discover. So we thank you so much for your presentation. Are there any other further questions from the group? Okay, well then let's.
I've got one maybe.
Yeah, go ahead, Jerry.
Yeah, you said you can detect the difference between like a gamma ray and a cosmic ray from the components of the shower, the atmospheric shower. So how are those showers different? Other than
yeah. So it depends. Depending on whether the initial particle is a gamma ray or a proton, will determine what kinds of pions are involved in the cascade, and then that will determine the relative fraction of different particles that you get on the ground. And so the way this is done would be by comparing the observed air shower to models of air showers for different types of particles.
Okay, because I noticed you said that they sometimes produce Cherenkov radiation, and that's also common with gamma rays, and that in itself would be indistinguishable then between them.
But the kind of the distribution isn't indistinguishable. There's different different patterns of the shower. The shower develops differently depending on what the original particle was.
Very good, very good.
Excellent.
Thank you very much.
Excellent presentation. We enjoyed that very much, Dr. Plant. So let's give Dr. Plant a round of applause. Thank you.
Yeah, thank you for having me.
Yeah, we so appreciate it, and look forward to following your research in the future. So thank you very much.
Thanks.
Okay, I'm going to share my screen next, and we've got just a few announcements to share with you all. We really have a lot of activities coming up the balance of July and into August, as you can see there. This Saturday night, the 13th, out at Oak Grove Park, is the Astronomy in the Park. And in addition to Astronomy in the Park, the Nature Center is open with activities there. And if anybody's available, like to come out for either one of those, I know we need volunteers. So we wanted to ask for a show of hands if we can, folks. Anybody here, let me know by voicing or raising your hand if you plan to come out for astronomy in the park on this Saturday? Jerry, Casey, anybody else?
Hi,
Okay.
this is Eric. I'm planning on being there, but my recent health issue. We'll see if I can make it.
Okay. Thank you, Eric. Okay. Being the summertime, we've got a lot of folks out on vacation and such that we've got to get as many volunteers out as possible for that, so that the public is served. But we appreciate all you folks that are coming out.
Okay.
And then the week after July 27th, there's a star party at Highway 4. The conditions should be really nice for that. Nice and warm, and hopefully not too warm, some clear skies. So, and then as we go into August, August will be a great month because we actually have 3 star parties, August 3rd, the 24th, and the 31st, between high altitude parties and Highway 4. But you see there, I have a couple of them labeled as potluck with a question mark, because we've got our option of when we want to have our high altitude potluck. And so we've identified these dates of August 3rd or August 31st. And if those don't work out for whatever reason, we can also look at the high altitude party in September on the 28th. So very likely we'll be at the heliport and or possibly Peddler Hill. That'd be great to be able to get up there and spend a late evening and have dinner together. So stay tuned to the Google message board in your email for when we get that potluck and those high altitude star parties planned. Doug is hosting the August 8th general meeting, and he has for us a movie night. And this is going to be a really good one, a Cosmos movie entitled Decoding the Universe. Spoiler alert, I've seen it and it's excellent. I want to see it again, and I want us to talk about it because there's just loaded with the history of astronomy, the theory of astronomy, just so much to learn in watching this one movie. So stay tuned for that on August 8th. And I'm not sure if we'll do a hybrid meeting where we're in person out at the county office bed and or Zoom or just Zoom only. We'll talk about that and see. I mean, it's a movie only. Maybe it does make sense to do Zoom only meeting. Okay, August 10th, astronomy in the park, and then these other dates in August. Again, we've got a lot of opportunities to go out and observe in the warm summer evenings, and it's coming up. So that's our announcements. And one other is this slide should be familiar to you all. We're still taking pre-orders for the 75th anniversary t-shirts. So if you haven't put in your order yet, raise your hand, speak up now, because we're going to place the order in August. It'll be in the August newsletter, but we're going to, because we have to take a vote on it to approve the expenditure. So is there anybody here in the meeting that is interested in ordering a t-shirt that you haven't already given Doug your order? I know we got a lot of orders last month. Okay, hearing none, I think we can go with our orders the way we have them, Doug. So if we're here.
All right.
So we're good there. Okay, we're kind of coming to a close now.
Tim, I have a question. It's Casey.
Hi, Casey.
Hi. Is there not going to be that July star party at Lassen. There was going to be that joint Sacramento and Stockton astronomy something at Mount Lassen.
Yeah, it is still going on. Yeah, the Sacramento Club and the Stockton Club. Um, I didn't have any participants, but if somebody's interested, if you're interested, that is still going on. I can get you the information and connect you with the Michael in the Sacramento Club is kind of the leading that star party.
So you're not going to it?
I'm still kind of on the bubble. Michael Chapman and I were both undecided or fully committed. I'm still kind of at that point, so I'm leaving it up in the air at this point. So I'm not fully committed to it yet. But please don't let that dissuade you. That's if you're interested in going. From what I understand, will be provided some kind of free lodging and probably free entrance to the park as kind of complimentary for serving the in the star parties. And the night sky should be really good up there. So, yeah. Reach out to me, Casey, if you're interested. I'll put you in touch with Michael.
Well, Tim, I was going to ask if you could do the same for me too. I'm interested, not sure yet.
Okay.
Thanks.
I'll make a note to maybe get an email thread going to this so that we're connected with Michael and any plans that he's got and get any details that we need. Okay. That kind of concludes. I did want to share with you this image that I found on the NASA James Webb site. I thought it appropriate for July. It's red, white, and blue. It is a star that unfortunately they didn't tell me what constellation or the location of the star, but it's a protostar, a young star that's relatively young, hidden in the neck of this hourglass-shaped cloud of gas and dust. And I'll just read the scene here was captured with Webb's mid-infrared instrument. And the blue represents carbon-rich molecules, and red highlights the protostar and the planet-forming disk around it. And the white areas represent a mixture of hydrocarbons, ionized neon, and thick dust. So all that is the formula for forming a star. I guess as the protostar grows older, it'll continue to consume, destroy, and push away much of the cloud. And eventually, once it finishes gathering mass, the star will become much easier to see. It'll be just a normal looking star without all the gas and dust around it. So kind of neat to see a newborn star, and a patriotic one at that, huh? So, okay, well, with that, then I'll stop sharing and just ask if there's any other comments or discussion that you folks would like to. How'd you like that presentation? Did you learn something about cosmic rays?
You bet. You bet.
Yeah.
Fantastic.
Yeah. Good job, Eric, in getting that. Kathryn as a speaker, really top notch.
Yeah, you're welcome. Just FYI, she had mentioned that experiment you can do in your home with like the cloud chamber and seeing the particles come through the cloud. There's a lot of videos online of such experiment. So if you guys get a chance, it's kind of cool to see it. There's a number of them that use like a fish tank. Get the cloud inside the fish tank, and then you can see the particles pass through the cloud. It's kind of cool. So if you have time, take a look.
Yeah, sounds interesting. Maybe we should do it as a group sometime.
Maybe
That'd be good.
Yeah, it'd be fun.
Oh, and by the way, I'm not sure if my hand went up, but I will be out at Astronomy in the Park on Saturday with my scope.
Perfect. Great.
That's great, Mark, because Jerry is and Casey are gonna need, and Eric are gonna need the help out there.
Oh no!
All the rats have abandoned the ship. including me.
Good for you guys.
It should be good. Ann Geber, do you know if you're coming out to the park on Saturday? Okay, well, we'll find out. So, well, good. I look forward to seeing you folks at the next event or at the next meeting, the next Star Party, whatever it might be. And I enjoyed this meeting, and hope you did as well. So, if there's nothing else, I'll bid you adieu and give you back the rest of your evening. And everyone stay cool. It's still over 100 degrees here in Stockton. So.
Hey,
Yeah.
it's 56 degrees and foggy here at the coast.
You had to put that in there, didn't you, Doug?
Of course I had to.
You had to put that in there. Okay, well, I hope you get sand in your shoes.
I love you too, buddy.
Yeah. Okay. Well, thank you all. Good night.
Okay.
All right, good
All
night.
right. Good night, everyone.
Bye-bye.
Okay.
Leave.